if you have here an object at some position A. By the way, you guys can see the whiteboard right now, correct?
Yeah, now we can, yeah.
That's correct.
All right, thank you. So, okay, so object at position A, I can calculate then the kinetic energy of the object, which is, again, let me then write that down. Okay, so kinetic energy, which is, K, so it's equals to 1/2 times mass of the object times speed of the object at position A squared. Because technically what we have with this energy, right, it's position, dependent. So like, let's say, so when I'm talking about kinetic energy, that's the kinetic energy at that instant when the object is at the position A. Now, let's say this object has a speed of, I don't know, let's say 2 meters per second, and its mass here is, let's say 2 kilograms. Then this is equals to 1/2 times 2, ignoring the units quickly, times 2 square, right? So then I can have, this cancels. So basically 4 joules. So that's the kinetic energy. Now, if the object keeps the same speed and continue moving, so let's say gets to point B and it is moving with the same speed of 2 meters per second, in a way, then you can say that kinetic energy at A is equals to kinetic energy at B, because we can always assume that mass itself doesn't really change. To change the kinetic energy, you need to change the speed of the object. So think like this. So if you have this particular, well, let's say case, right, when the object has the same kinetic energy at points A and B, you can maybe assume that object doesn't change its speed. So same speed at point A and at point B. Now, it's possible that maybe between points A and B, it would slow down and then it will speed up again. Everything is possible. But let's say one thing we can say here is that the object has the same speed before and after. Usually that's kind of what we do in energy problems. We talk about some kind of two specific points, and then we compare, let's say, energy at point A to energy at point B, and then we can make some conclusions, right? So if kinetic energy at point A and B are the same, well, that means object has the same speed at those points. If, for example, I look at kinetic energy of B and say, all right, so the kinetic energy of B is greater than kinetic energy of A, well, that can only happen if it is moving faster at point B. That's why kinetic energy at point B, which is 1/2 times mass times speed at point B square, right, is higher. So if the kinetic energy is, increasing, that means object is also increasing the speed. So that's why more important is not kinetic energy at some one point or another point. More important, let's say, as a physical quantity, is changing kinetic energy. That's what we have as a, let's say, way of looking at the motion, looking at the delta K. See, if the delta K, which is kinetic energy at point B minus kinetic energy at point A, right? The kinetic energy difference between those 2 points, can tell us a lot of things about the motion. See, as I said, right? If we calculate this and we get 0, which means delta K equals 0, means KB is the same as KA, which means speed at point A and B is exactly the same. So this is a uniform motion. So it's a uniform motion. What else do we know about uniform motion? No acceleration, net force equals 0, and so on and so forth. That means we can look at this changing kinetic energy and use that to understand the motion. Now, if I have then delta K greater than 0, which means, it's a positive quantity, it means that if I'm looking at KB minus KA, well, if it's KB minus KA is greater than 0, that means KB is greater than KA. What does it mean? Well, it means speed at point B is greater than speed at point A. Well, it means then there's acceleration, there's a net force, and so on and so forth. That means, again, we can look at it in terms of using this energy of motion, right? Kinetic energy at 2 points, figure out what happens to the object. One of the advantages for using this is that when you're calculating kinetic energy, you don't really use any vector notations. Kinetic energy is a scalar quantity, means that meaning that if you're using this v here is the speed, not the velocity. It doesn't matter in which direction it is moving. I can have the b to be right here instead of there. So technically then it's moving to the left, right? But still, I'm going to get exactly the same kinetic energy, exactly same change in kinetic energy, and exactly same information. That means it is, if kinetic energy at point B is higher, it means object is speeding up, just moving to the left. Okay. Any questions? All right, so now another question is this. Okay, so let's say the object here is at point A, moving at some velocity 2 meters per second. And let's say it gets to point B, and let me do it here. So let's say here's this object at point A, and let's say object, or thing like this. Let's make it a little bit easier. So let's say object is at rest at point A. Now, one of the things we can do here is we can say then, all right, so then kinetic energy of the object at point A here equals to 0 because it's not moving. So if your total energy of the system only in terms of kinetic energy, because it doesn't have to be kinetic in terms of kinetic energy. Hopefully you already know that there's also, for example, gravitational potential energy. There's also, let's say, elastic potential energy, right? So the gravitational energy is based on height. Elastic energy is based on the shape of the object when it's, stretched or compressed. That means the total energy is the sum of all the different type of energies at that point A. And let's say if object has no height or no elasticity, then total energy is just in terms of kinetic energy. Let's say this point at point A. Then one of the things I can do here is this. All right, so if kinetic energy is 0 at point A, that means total energy is also 0 at point A. How do we make then the object to gain energy? That means if in order for the object to move, we have to give it an energy because it doesn't have any energy, not even energy to transfer or convert from one type to another. It doesn't have any energy. So then in physics, this work, this word work is basically used to represent the way of transferring energy into the system. And it's a mechanical way of transferring energy. Because later we're going to see that there are other ways of transferring energy too. You can transfer energy as a heat, which is due to change in temperature. There are other ways that you're going to learn in the later chapters. But right now, this is a mechanical way of transferring energy. And if you're doing this type of transfer of energy, we call it work. And we use capital W to represent work. And the way then we transfer energy into the system, with this mechanical way, right, is applying some kind of force. So let's say you apply some kind of force, and this force then will make the object move from point A to point B, which you can probably visualize, right? So you have an object just sitting there at rest. In order for us to make it move, we're just gonna have to push, right? And if you push with some force, and then there's a displacement, right? Then we can say that we did work, meaning that we transferred energy into the system. So then the work done is equals to, the general equation is an integral of force dot dx, and this is basically dot product, which hopefully you will learn in the lecture, or probably already learned in the lecture, right? So f dot dx, and pretty much you can write it like this. It's f dx. So if the force is constant, and by the way, the limit here is going from x1 to x2, which is, x1 is point A, x2 is point B. So that's the equation for the amount of work done. For example, if this force here is 20 newtons and the delta x here is 5 meters, then in a way, one thing you can, you want to look at it here is that if the force is constant or not. If it's 20 newtons the entire time, That means it's constant. So you can remove that from the integral and then say, all right, so then I'm going to go from 0 to 5 meters and integral of just basically dx from 0 to 5. Then this becomes F times delta x, which is 20 newtons times 5 meters. So then you get 100 joules. What it means here is that as the object moved from point A to point B, when 20 Newton force applied, to the right on the object, then amount of work that was transferred into the system was 100 joules. Okay. That means this is, again, amount of work done, which is integral of F, let's say F dx. So I don't make it like a dot product. Let me just do it like F dx, going from x1 to x2. Okay. This is the equation. Now, one other way we can look at it is basically this. How is this related to the, let's say, this kinetic energy of the system? Well, work kinetic energy theorem then tells us that work is equals to the change in kinetic energy. Because if the object is at rest at point A and you apply force, then you basically making it move. And by, if you push it all the way to point B, then you're changing its kinetic energy. So as you change kinetic energy, by how much kinetic energy will be, changed, exactly equals to how much work you will do. That means you can say then delta K here is equals to 100 joules. That means we transferred 100 joules of kinetic energy, 100 joules of energy into the system, and that all went into kinetic energy. So that's why this equation, right, work is equals to delta K, is pretty much the equation that we're going to be using in this particular lab, because this delta K, which is the change in kinetic energy, will be due to the fact that there's a work done on the system, and the work done means that mechanical way of transferring energy to the system. And if the system gains energy, it can then use that energy to move faster. Okay, so we can say then work done is equals to KB minus KA, where A is initial, B is final. For example, if then this guy here was 0, because there was no kinetic energy to start with, then in a way what we can do, we can say that work done is equals to kinetic energy at point B. That means at point B, the object is going to have exactly 100 joules of kinetic energy. And remember, the kinetic energy equation then is equals to 1/2 mass times speed B squared, which means finally we are looking at the equation that relates the work done to the speed, which is equals to 1/2 m times speed at B squared. And this is one of the important equations that we're going to be looking at in this lab. That means if we try to investigate, let's say, this relationship between work done and the speed, according to this equation, work done is proportional to speed squared. Or you can just go other way around and you can say that the speed is proportional to square root of work done, right? Looking at, taking the square root of both sides, you can kind of look at it. And 1/2 m is just a constant, right? So that means we are going to be looking at those two relationships. That means we can either look at it in terms of work done proportional to speed square, or speed is proportional to square root of work done. That means if I am looking at the graph of work done versus speed, for example, if I do work done versus speed, let's say work done versus speed, what type of graph do you guys think I will get if I do work done versus speed? What type of graph will I get?
Parabola?
Parabola, exactly. Because work is proportional to speed squared. So if I'm doing work versus speed, I'm going to get parabola. So what do I need to do in order to linearize this graph, for example? That means find the relationship where if I'm using work and speed, such a way that I'm going to get a straight line, linear relationship.
You could plot work squared and speed squared, or you could plot speed and the square root of work.
Exactly. So I have two options, which you also have two options when you're doing the lab. So you can plot either work done versus speed square, and that's going to give me a linear graph. Or I can do square root of work done versus speed, like you can see over there, and I'm going to get, again, straight line. Yes, perfect. That means if you do work done versus speed, which you should do initially to see that it's a parabola, then one of the things I want you guys to do here is when you're doing this graph, take a screenshot of that. And then when it later asks you to do the linearized graph, so then you have a record of that, and you can just basically use this, screenshot to include in explanation where this was my graph before. And then in order to linearize, these are the steps that I took. And final graph that you're going to leave in a pivot should be the linearized graph. So work done versus speed square, or square root of work done versus speed. Okay, so either one of those. Again, you're going to get exactly the same thing, so it doesn't really matter which one you use. Right, any questions? All right then. So let's go to, all right, let me open the lab quickly. All right, there you go. So you can see, right, as the learning objective, we'll explore the relationship between the work stored in the spring and then the velocity at which that spring can launch an object. Now, the work done, let me quickly go back to here. I want to, show you in terms of work done equation. So remember, so work done was integral going from x1 to x2 f dx. All right. So if the force is constant, then this just becomes simply F times delta X. And if the force has an angle with respect to horizontal, then you can also have a cosine of angle theta. Okay. So this is for constant force. One of the things we're going to do here, though, we're going to work with this force that is not constant. So think like this. If you have a spring like this, which sits in equilibrium, when the spring is in equilibrium and you take the spring and start stretching from equilibrium, then there is this restoring force. So let's say if you take it and start stretching from equilibrium, there is this restoring force. Usually, we call it spring force. And this spring force always points in the direction of the equilibrium. That's why it's a restoring, because it's trying to restore the system back to equilibrium. So more we stretch, stronger the force. That means this spring force is not a constant force. It's proportional to the distance x from equilibrium that you stretch. Okay. And the equation then for the spring force is equals to negative kx. All right, so have you guys seen this equation already? Anyone? Have you guys, what is the equation of, what is the name of this equation?
Hooke's law.
Yeah.
Yes, thank you. It's Hooke's law. So this is Hooke's law, which relates spring force or restoring force to the distance that you are stretching or compressing. Okay, so this is, F spring equals negative kx. And you can see, right, this force is not constant. X is 0, force is 0. That's why when it's in equilibrium, there's no restoring force. When you start stretching or compressing, then this force starts increasing. More you stretch, stronger it is. Now, then, but still, right, it's a force that changes object's position, so then technically it can do work. So then what is the equation for the work done for this? This is for the spring force. Well, it is still, you're doing F spring, dx, right? Going from x1 to x2 using this equation. Then this becomes integral Well, I replace force with negative kx, going from x1 to x2, then so negative kx dx, which means then I can remove negative k, but I cannot remove x. So what I have to do then, I have to then integrate this. So it becomes negative k 1/2 x squared, right? Then from x1 to x2, which means then the work done by the spring force is equals to 1/2 kx1 squared minus 1/2 kx2 squared, where I integrated implemented that negative. So, and this is then the equation for the work done by the spring force. Okay, so generally what we have here is we can kind of simply write it as work done by the spring force equals 1/2 kx, let me be like 1/2 k delta x squared, where delta x is basically the displacement from equilibrium. Since 1 point always came, is equilibrium, so it's 0. So then you can calculate, this quantity. So that's the work done by the spring, 1/2 k times delta x squared. Okay. Any questions? All right, so then what we're gonna do here is we're gonna then be able to ready to go back to this lab. Okay, so we're gonna, you can see, right, relate the work done by the spring to the speed of an object. Okay, so and our object is basically, you can see, right, a card with a sitting Einstein. Okay, now this let's see if I come back here, you can see, right, this particular experiment has 3 different sort of, like, let's say, a point of view. So we have the entire event shows a regular speed view of the stretch and release. And this meant to provide a context for the event, but not opportunity to make precise measurement. That means I'm going to show you right now the entire event, but we are not taking any measurement with that video. We're going to then concentrate on 2 different videos, which is basically the video breakdown into 2 parts. One is a spring stretch view. The other one is release view. Because if you look at the entire one, you basically have both of them together. So for example, right now I have 602 gram spring stretch 1 and an entire event. So I'm going to load that and see what we have. We have an unstretched spring, and it's connected to an object by a string. So when we pull the cart and Einstein to the right, we also stretching the spring. Then when we release, the spring force is gonna pull the cart to the left toward equilibrium, and the object from rest is gonna start speeding up. From the energy point of view, you can say then object had no kinetic energy, and then once you release, then the spring force is gonna do work, transfer energy into the cart system, right? And the cart is gonna start speeding up because of that. So let's look at the video. There you go. So this is the entire event. So pay attention to how we start from here, how we then pull the Einstein. So now you can see, right, see where the spring was and now where the spring is right now. So the spring is being stretched, and that means there's now stored energy. So once we cut the string right there, then that stored energy, right, then the spring gonna do work, and that work gonna then be transferred into kinetic energy, right? That means that the transfer of energy will allow the cart to start moving, and gain some speed. All right, we're gonna then have 2 different videos, spring stretch. So this one is we're gonna do first. So along with the upper ruler, we can measure, we can make measurements, right, of the amount of the spring stretch before the cart is released. That means, for example, if we go and look at spring stretch for the same mass, you have to make sure you always keeping the same mass, same stretch, spring stretch quantity value. So this is going to be only for the part where the object going to be, let's say, released, right? Actually, no, this is only when it's going to be stretched. So here's the video. There you go. Again, I want to make sure that we all on the same page on one thing. See, this is what I'm using to do the demo. And if you go and change this, you can see, right, you have a lot of options. So please do not use the same one as I'm using to demonstrate the experiment. So the measurements that I'm going to take, the ones that you actually start making, right, you can just try to choose differently. There is a portion of the experiment where it's asking you to calibrate using the one that I'm using right now. By all means, you do it for this part. But then when you go, let's say you have to lock this and then go to the next part, try then, using different value. All right. So, for example, right, to calibrate, to learn how to make measurement, we're going to do this. Starting from here, which is where the object or the spring here is at rest, we're going to take a ruler, and there are two. Here's a small one, and you can see, right, it doesn't go above, like, let's say basically it doesn't go above this point. And so we don't use this right now. And there's another one right here that specifically for this part. So I'm going to put the 0 where the spring is, like that. And then I'm going to then play the video until we stretch the spring to some maximum value. Okay. All right. So who can help me? What do you guys see for this stretch distance? What will be the stretch distance? Anyone?
Looks like 6.5 centimeters.
All right. Anybody else agrees with that? So basically somewhere over there, right? All right. 6.5 is correct. Thank you. Now, that means you're going to come over here and pretty much answer a couple of, multiple choice questions. So over here, what value did you measure? And pretty much, you're not going to be able to, have 4 submissions until you get it right. Okay. So that means, you try until you get the right one. So you learn how to do that correctly. All right. So here's then what we have. Any question on how to get the stretch distance? Okay, then next we're gonna go to and change it to release. And we're gonna try to measure, let's say, this time we don't use this one, we use this guy over here. So our goal will be to measure the time it takes for the object, you can see, right, that green dot, which I'm gonna make it as my reference position. How long does it take for that green dot to move 15 centimeters? Now, where's 15 centimeters? Well, it's right here. Starting from here. That means how long does it take for it to cross that distance? Now, how do we do that? Well, there's a timer over here. So we're going to take a timer and I'm going to reset the timer. But I'm going to do this. So I'm going to find instant when it's being released. So okay, clearly those points now are off. All right, so going from here to there, let's say. Okay. All right, so see if I start from here, see the timer already started, but the card hasn't moved. Okay, so that's what we have to do. And it tells you over here, right? So basically Um, in terms of this, we have to find the time it takes for it, to move. But here's what we have to do. See, if I do this, right, if I go back and measure this, see, it starts from rest and it starts speeding up all the way like that. And that's not what I want. I don't want to find, let's say, how long does it take for it to speed up? Because initially, when we cut the string, spring force is pulling the cart. That means the tension, right, is pulling and it is speeding up. What we need to do is go back and find the position where the spring is no longer pulling. That means this, the string is no longer stretched. So if you can see, right, if you watch the video, see, now it's slack. So right now, when it comes back to, see, it's the string. I mean, I'm talking about the string right here, the one that is pulling the cart. So it is right now still under tension. And I need to find the one where basically the spring is back to equilibrium already and it's no longer pulling, right? Maybe somewhere right there. Okay. Now, why do I need this? Well, think like this. The cart has been speeding up to this point. From this point on, because the string is no longer stretched and pulling, but it's slack, the cart will be moving with the final speed that it had when it was pulling. That means from this point on, it will no longer speed up, but maintain the same constant speed. That means now I'm going to reset my timer, and now I'm going to measure how long it takes to go from here to there. Because at this point, the motion of the cart is going to be uniform. It's not going to, let's say, it's not going to speed up, and it's not going to slow down. It's going to be moving at constant speed. But I don't know what that speed is. But I have a way of finding that speed, and it's easy for me because if it's moving at constant speed, all I need to do is find this distance, which I have, right? 0.15 meters. Then find how long does it take, and then delta x over delta t can give me the speed. Because if it's uniform, that's all I need to do. Find the time it takes for it to cover that 15 centimeter, and I can calculate the speed. That means I go back, play the video, and more or less stop over here and kind of go back and then measure the time. More or less about 0.35 seconds or something like that, right? Give or take. You'll probably be more accurate. But this is what I have. Now imagine, right? 0.15 divided by 0.35 seconds should give me then the speed. Okay. And this is in a way that speed VB that I was talking about in the pre-lab lecture. Because remember, VA was 0 because it starts from here, right, with rest. And then VB will be the speed that we get from here. And that's how we get the speed. Right, any questions? All right. You guys are awfully quiet today. I don't know if you understand everything or confused at some point, but remember, this is the time to ask questions if anything is confusing. So release and stretch, those two videos. Okay. Then you're going to basically answer some of these questions over here. Then what we're going to do here is come back, after this, right, you're going to log the answers and continue. And now you're going to basically start doing your own measurement. That was just for the calibration, for learning how to do measurement. Then here you're going to choose your own. So let's say you can do like, stretch 2 or 3 or, 702 gram and thing like that. Okay. So again, I'm going to do 602.1 and I'm going to go to spring stretch first. Okay. And then so what you're going to do here is basically that, right? So you have stretch 1, stretch 2, stretch 3, stretch 4, stretch 5, which is, you can see, right, you have those. Well, I guess, if you're using 602, you can do that as well. Well, that's fine. You can use any mass, just, um, I guess, I'll just use in terms of this one, and the rest you're going to basically do it on your own anyways. So you're going to take data, and I already have the table, as you can see, right? I already have what columns should represent. So this is, what is this spring stretch for this condition? That means exactly what we did before, right? So let's say if we did this one, well, we need to, let's say, take this ruler, put it there, play. And as we agreed, this is more or less about 6.5. That means you're going to go back here and say, this is 0.65. 0.065 centimeters, right? Oh, actually, it's in the centimeters. Never mind. So 6.5 centimeters. Okay. Then, for example, here you are given what is the spring constant K, 26 newtons per meters. Because remember, to calculate the work done by the spring force, it's 1/2 K times delta X squared. And delta X is the stretch distance. That means in this case, if the stretch distance is 6.5 centimeters, then you can calculate the work done. One of the things you want to do here is to understand when you're doing work done. So technically, you want to maybe convert everything into meters. So I actually recommend make another one here and say that, okay, so it's a spring stretch in meters. And let's say here's the quantity, let's say X. Now, one of the things you can do here is you can just convert it directly, or when you have more values, easiest way to do, like let's say formula. Remember, going from centimeters to meters, right? You take then, spring stretch, and which is the quantity in centimeters, and divide by 100, and that should give you in meters. And you can write this value now in meters. Then come back for the work done. Then here you can say change the column, formula. Remember, formula is right here, right? 1/2 K times delta X squared. So you can say it's 1/2 times K was 26, right? It was given to you. Then times spring stretch like this in meters squared. So square like that. And if you submit, then you get the work done. All right, any questions? How you get the work done? And let's say when you go to the second stretch, let's say if you go here, do the second one, then you measure that as well. And you can see, right, you're going to get a different one this time. If you have a, if you go to the second one, there you go. You can see, right, it's no longer 6.5 centimeters, something like that. That means you're going to get a different value, then convert to meters, then calculate the work done. Then this is for the spring stretch portion of the experiment. So you're going to do 5 different, right, measurement of the spring stretch, calculate, convert it to meters, then calculate the work done. Then go to the second video, which is release. Then do the same thing for this portion. That means what you do here is you wait until the string is slack, right? So it's not under tension. Put this guy there and measure the time. So put this here, measure time, and that means, your delta X all basically going to be 0.15. 0.15 and so on and so forth. And then you calculate the time. So for example, if, even though it's a centimeters, you can change it to meters. And let's say this point takes 0.3 seconds or 0.3 seconds or 0.4 seconds. Then you can calculate the speed by doing then delta X divided by delta t. And then that's your speed. And then what you're going to have here is you're going to have then work versus speed. So then you can come back and then do this first. Again, so don't worry about whatever I have right now. It says velocity and the spring stretch, right? You're not doing those. You can just change it any way you want. Remember, we're doing speed, work done, type of relation between spring and work done. So that means, for example, if I do here as a work done, and then here if I do speed, okay, I have just one data point, but let's say you can see, right? If I have more data points, I should get, parabola. So this is the graph that you want to do first. And then when you go to the other parts, then you're going to say, all right, so here you can see, right, what the relationship between the initial work done and the cart and the velocity. And then you may need to linearize this data. So then you can try to linearize. And this is where you can take a screenshot of the work versus speed to include that, then change it to work versus speed square, for example. All right, any questions? All right. So then finally, we have one other part. This is the last part of the experiment, checking the spring constant. Remember, the spring constant was given to us, but we can also do an experiment to check the spring constant. Okay. So this experiment is actually something that we used to do in a let's say, physical class environment. It's relatively straightforward. One thing we have here is, so there is a force acting on it, right? And this force that's going to pull the spring is basically equal to the amount of weight, because you can see, right, the object is always going to be in equilibrium. So the gravitational force and tension force, like F of t, are equal to one another. So F of t is equals to, let's say, then mg. And F of t is the force that, Hooke's law, right, equals k times x. That means the force that stretches the spring is the weight of the object hanging on the other side. That means, if we change the force, we're then changing the distance, because Hooke's law tells us that force is proportional to distance. That means we also looking at this relationship. Okay. So then if I'm looking at this, the experiment itself is going to be relatively straightforward. So you have then, let's say, trial one. So you add mass, spring is stretched. That means you can stop and come back here and say, all right, so this is going to be my force, and in newtons, and let's say F, and let's say this is going to be my distance, units of meters, for example, and let's say X. So the force, again, is going to be based on how much weight you have, and you can write each mass, each disc is 100 gram. Right now you have 100, only one over there, so it's 100 gram. In a way, you can say then, let's say when it was 0, this was 0, but when it's, let's say, 0.1 gram, or well, actually what you have to do here is this, remember, so it's 100 gram. To get the force, you have to multiply that by 9.8, right? So mass, so remember, so gravitational force is equals to mass in kilograms times g, which is a 9.8 meter per second square, right? So that's basically gives you Newton. That means take how much mass you have in grams, convert to kilograms times 9.8, and that will allow you to find the force. If you really want, and hopefully at this point you're probably comfortable more already with working with pivot, you can make a column to the left of it, for example, and say this is mass in kilograms, let's say m, right? So then here you can say that, all right, so when mass is 0, let's say how much you're adding extra, right? That's 0. But then when this is 0.1, then this guy, the force, is going to be the mass times 9.8. And that can give you the force. All right. And then measure the distance when you have this. Finally, at the end, you can then plot force versus distance and get a graph. For example, if this is 0.2, let's say 4, and things like that. So you're going to get something like this. So you find how the force and distance related. You can do this and see if there's a linear relationship or not. Okay. So because the force is equals to k times x, you should expect a linear relationship with force increasing as the x is increasing, or x increasing as the force is increasing, because of the Hooke's law gives you direct linear relationship between those. All right. So then when you do the graph, when you find the fit, then let's say this is your equation. And because of that equation, right, then who can tell me, how can I find, if I plot this, how can I find then the spring constant K? How can I find spring constant K if I plot force versus distance?
Slope.
Exactly, the slope. So which is right here. Again, remember, I made up those numbers, but when you do your own, this A should give you then the slope of the line, and that slope should then represent the spring constant K. All right. That means this lab basically has kind of two parts. One, exploring the relationship between work and kinetic energy, or work and speed, using this experiment, right? The second one, finding a spring constant K, basically using Hooke's law experiment. Any questions?